Hello. Okay, thank you for the introduction and thank you for the invitation. I would like to begin with a question. So, how many of you are familiar with the Big Bang Theory, the concept of the Big Bang Theory? Please raise hands. Okay, excellent. So that's essentially all of you. So this theory states that the universe, the forces of the universe became into form for the explosion of singularity. That explosion also formed the building blocks of our universe. It's essentially the beginning, neutrons, and then later they developed into electrons, and protons, atoms form together molecules form gas clouds, and gas clouds eventually gave rise to galaxies. The galaxies formed planets, stars, and ourselves. Now, that depicts the global Big Bang. Now, how many of you are actually aware of another Big Bang that underlies our own development? And I don't refer to the events leading to conception. So, now seriously, the notion that I would like to talk about today is the events that leading to our own creation. And this process begins with the pluripotent cells. You can see them there in the middle. And these pluripotent stem cells reside in that small white pixel that you can see on the left-hand side, enlarged on the top. On the right, you can see a human embryo, actually a fetus already, that developed within 3 weeks. And what's very evident about this fetus that it emerged into being within 3 weeks. We can see all the tissue types that our bodies consisted of. We can see the head, the brain. We can see the spinal cord, the heart, and so on and so forth. Now, what happens in this interval between the pluripotent cells and the embryo is essentially a Big Bang event. That's what creates us. And what's going on actually is that these pluripotent cells, when they differentiate, they begin to express different sets of genes that are necessary for the creation of these cell types. So let's see how this works. So you can see at the top a nucleus of that illustration of a nucleus that exists in our cells. And within this nucleus, there's genetic information, and the genetic information actually encodes for the creation of a human body and also for the maintenance of the human body throughout life. I think a nice way to illustrate that is essentially that all of the cells of our body contain the same information, but actually the expression pattern of the genes actually what determines the different cell types. So, for example, the gene that encodes for insulin is present in all of our cells, but it's expressed only in pancreatic beta cells. So pluripotent cells stands at the base of this process, and then the different gene expression patterns determines the differentiation process. Now, what underlies our own development is indeed this Big Bang, and what we are interested in is the landscape of these developmental cells. We call them developmental progenitors that give rise to us. If we understand this, I think that we'll have very important understanding into phenomenal questions that actually, fundamental questions that concerning our own development. Now, what we think that is going on through this Big Bang process is actually the formation of progenitors, and not progenitors for tissues like blood and heart. So, a nice way or easy way to illustrate that is that to think about the tree. And the tree, when it develops, it forms branches, and these branches gradually differentiate into, or develop into differentiate the cell types. So not directly from the pluripotent cells at the bottom to blood progenitors, heart progenitors, brain progenitors, but a gradual process of differentiation. Now, to recap on the question, what we are interested in is what is the repertoire, the landscape of developmental progenitors that emerge through this Big Bang event. If we understand this, we will actually be able to contribute quite a lot, I think, to also treatments, as I will demonstrate later. So now, in order to understand what are the different progenitors that emerge through this Big Bang process, we need to start with an experimental model. And the experimental model that we work with are pluripotent stem cells, as shown here in the middle. These pluripotent stem cells were derived for the first time in 1998. from fertilized human embryos, and they were cultured in a way that allowed them to culture indefinitely and also to differentiate to all the cell types of our body. They're called human embryonic stem cells, shown on the left. In 2006, an extraordinary experiment was carried out by Professor Yamanaka from Japan. He transferred some of the genes that are expressed in embryonic stem cells on the left into somatic cells. And that have created, actually, a very interesting phenomena. It actually reprogrammed the cells. It reverted them to the embryonic state, meaning that they are now able to give rise to all of the cells of the body and also to maintain themselves in culture conditions for an indefinite amount of time. So essentially, we have now a system at which we can study these big bang event in the culture. Now, these cells that we have that have been derived for the transfer of genes from the pluripotent cells to somatic cells is called, the process is called reprogramming, and the resulting cells, we call them induced pluripotent stem cells. Now, the hope is that in the future we'll be able to derive from these pluripotent stem cells, from the induced pluripotent stem cells, cells that will not be rejected by our immune system if we inject them to our cells. And the reason is that they are cells of a self. If you are deriving pluripotent stem cells from individual, from myself, for example, differentiating them in a tube to heart cells, for example, we'll be able to return them into the same individual without tissue rejection. And that's actually what we are trying to do in the lab. On the left-hand side, you can see human fibroblasts. Fibroblasts are cells that are taken, for example, from our skin. So we need a tiny skin punch in order to grow the cells on the left-hand side. And then by transfer of these reprogramming genes, we are able to form these beautiful colonies. The pluripotent stem cells go in colonies, as you can see on the right. These colonies induce pluripotent stem cells. And now that we have them in culture, we can start studying how they differentiate and form these developmental progenitors. Now, we need to remember that these human pluripotent stem cells, induced pluripotent stem cells, are actually a proxy for human embryos, and the way that we induce their differentiation is by applying factors to them. We call these soluble factors or growth factors. These growth factors are present also in embryos, in human embryos, for example, and by applying them to the cells on the top, we can induce their differentiation. So you can see here a gradual differentiation process from human pluripotent stem cells to mesoderm progenitors to cardiovascular progenitors. Now, mesoderm is a funny name that you don't need to remember, of course. What you do need to remember is that from mesoderm progenitors belong to this landscape of developmental progenitors, and the cardiovascular progenitors are derived from them. And cardiovascular progenitors may have important utilities in regenerative therapies, because cardiovascular, of course, mean that they are belonging to the heart lineage. So I would like to describe now an experiment that demonstrates the regenerative capacity of these progenitors. This is an experiment that we carried out in collaboration with Stanford University. And what we did here is to introduce the human pluripotent stem cells derived cardiovascular progenitors into human heart environment. But we did it in the mouse. So we took small pieces of donated human hearts, placed them in the mouse ear, as you can see on the top, enlargement on the bottom. And then after the heart was received and actually we saw beating of these pieces, we transplanted these cardiovascular progenitors into the human heart environment, and the cells were labeled with a green fluorescent protein in order for us to be able to track them. On the right-hand side on the top, you can see the result after a month. We were struck by the results, because you can see that actually the transplanted cells that we've derived in a tube from human pluripotent stem cells actually differentiate into functional cardiac progenitors. That's, I think, a very strong demonstration of this technique, that we actually can differentiate the cells into progenitors, the progenitors into cardiac progenitors or other types of progenitors, and regenerate the heart tissue. Now, the other notion that I would like to discuss today, that of course that pluripotent stem cells are wonderful because we can perhaps in the future regenerate tissues with them, but they can also act as time machines, and I would like to explain this notion. So clinicians often encounter disease that are very difficult to cure. They can actually try to treat them, but not to cure. And that's true, for example, for congenital diseases on the right, for damage to the heart myocardium following heart attack, and for Parkinson's disease, of course, as well. These diseases are difficult to cure. Now, imagine that we were able to travel back into the past and study the molecular aspects of the disease before it develops. And that's actually something that we can do. We can produce iPSCs from patients like Michael J. Fox and study the generation or the early defects that lead to his disease. By doing so, we can probably analyze in a better way the genetic defects leading to his disease. And then we can travel back to the future and then provide better treatments. Now, this concept is actually well developed as well, and that's what we do in the lab. I'm sorry for this, this is in red. So we isolate cells from patients like Michael J. Fox, culture them. You can see the pluripotent cells, the induced pluripotent stem cells that emerge in the tube, and then forward differentiate them to these progenitors. Now we can study the disease on the progenitor level. You can see the progenitors here on the left. Another very important notion concerning studying disease is that we can study individualized disease. And the reason that is important is because due to environmental factors, due to different genetic backgrounds, we are all different. For example, the disease that Michael is very different probably from Muhammad's Ali, the underlying pathology, the molecular pathology. And by analyzing iPS cells, induced pluripotent stem cells, and analyzing them then in the tube, we can come up with a personalized medical tool. So studying Michael's disease in separate way separately, and then repeating perhaps the process for Muhammad Ali. Now, I would like to go back to the Big Bang hypothesis in order to make one final and important point. I would like to discuss, again, the Big Bang. So the Big Bang created the building blocks of our universe, but this Big Bang didn't come with an instruction book, handbook for creation of the universe. It generated the forces, but not the information. So a manual handbook is missing in the Big Bang. Now, in our own creation, the embryonic Big Bang that generates the progenitors that give rise to us, there is a handbook. The handbook is within the cells that create the initial cells, the pluripotent cells that create the differentiated cell type. So again, the embryonic explosion is all about information. Now, take a minute to think about it, to reflect about it. You and everyone that you know generated yourself from a single cell. And that's quite an admirable, I think, achievement. So your mother provided you with environment, provided you with the nutrients, protection, but it is you that created yourself from the genetic material that was embedded in you by your father and your mother. So essentially, we are machines that we are self-creating. We have created ourselves. And we tend to think about difficult tasks that we carry out on a daily manner, about graduating school, getting tenure, about financing a house, for example. But what about creating yourself? I think, at least to me, this is one of perhaps the most difficult task that I have ever achieved, and probably also for you. And that's why I found pluripotent stem cells so amazing, because they allow us to study how we create ourselves. So let me show you a bit about the approach that we are taking to analyze the way that we create ourselves. So we can treat these embryos, these pluripotent stem cells, embryonic like cells, as an operating system or electrical circuitry. That's what they are, essentially. They are little machines. And you can see on the right-hand side a depiction of the processes that we think actually controls the early differentiation of pluripotent cells. Now, we can now intervene with these processes by you can say, playing around with these molecular cascades and changing them in a way to see if we can enhance or reduce the formation of certain cell types. So, for example, we can intervene with one of these nodes in the circuits and then see if we can get more cardiovascular progenitors or less in the culture. And that's, of course, in the future, will be important in order to generate transplantation products. So pluripotent stem cells are very important by probing them to be able to manipulate them in a way to generate the cells that we are interested in. Now, I would like to come to the end by saying that we all should love generation because pluripotent stem cells actually allow us to do three major things. They allow us to study this embryonic Big Bang, the process that give rise to the cell types that we are consistent of. That will be very important in the future for the creation of tissues for regenerative treatments. They also, the second revolution that actually they carry is the fact that they can act as a time machine for us to be able to study our own development, and also for studying human disease on the molecular level. I'd like to finish again now by thanking Yona Rusha that generated most of the data that I showed, and Dmitry Shaposhnikov for generating the illustrations. Thank you so much.